Hi there, welcome back to the formulaic approach. Now in this video we are going to be talking about current electricity. I'd like you to stick with me from the beginning to the end because in this video I'm going to unveil a lot of things about electricity. So if you don't know anything about it at all, you should stay till the end, okay? Because it promises to deliver as much information as possible and take you from zero to hero, I mean, or partially hero, when it comes to current electricity. But I also promise to release another video for A-level students. But if you are an A-level student and you don't really have a good grasp of current electricity, you have to start from here, okay? Take this course first, then before you move to the advanced level, okay? So understand this is just basic current electricity, but it promises to help you to solve as much O-level questions as possible, WAEC, JAMB, etc. Okay, IGCSE. So now, in this video, we are going to be looking at current electricity, like I said. So current electricity is the aspect of electricity that basically studies moving charges. You know, there are two aspects of electricity. There is electrostatics and there is electrodynamics. So electrodynamics is current electricity. When we make mention of current, we especially mean that charges are moving. And that is why we describe current or define current as the rate of flow of charge. Current is defined, current is the rate of flow of charge. However, that is just that is steady current. This is steady current. So there is average current and instantaneous current. So that is what I'll deal with in A-level course. I'm going to show you what instantaneous current is and what that is we looking at current in the microscopic scale. But let's see how far we can go with current electricity today. So like I said, current is the rate of flow of charge. So when charges are moving, we say current is produced. Current is produced. Keep in mind that there are two charge carriers, the protons and the electrons. So within the material nature of matter, the atomic nature of matter, it is electrons that actually move, not protons. So when we say electricity is being conducted, current is passing through a conductor, then we mean to say that electrons are moving. Now there are two aspects of current electricity. We have the direct current known as DC, and we have the alternating current known as AC. Direct current is the aspect that covers current that flows in one direction, while alternating current covers current that flows in two directions. So why do we call that one direction? So we have what is called a circuit that looks like this. This that you see, I'm still going to elaborate or expound on it. Now, if I have a load here and I connect it to a battery like this, direct current is the one that studies this current moving in this direction and back to this place, back to the battery. So that's direct current. But alternating current is one where the power source is quite different. It's not a battery or a cell as you see it here. The power source is actually also alternating. Okay, so because of that oscillation is why we have the current being produced by that source also alternate or oscillate. Is that clear? So it's changing direction for alternating current and it's going in just one direction. So it's a unidirectional flow for direct current. And the circuitry is very simple. It is simply there is a load, usually very simple. There is a load and there is a power source. So that power source is typically a battery in most cases, at least for the two terminal devices that are going to study under current circuit, current electricity. You are going to be dealing with a battery as power source most of the time. So in this video, we are covering just DC. Before we can cover AC, we need to cover magnetism and all of that. So that's why we're dealing with only DC. But a good knowledge of the DC helps you to be able to overcome problems in AC as well, right? So let's go on. So like I said, we are covering DC. Now what are the sources of direct current? We have the battery, okay, which is chemical. So where chemical energy is being converted in a battery, for example, chemical energy is converted to electrical energy. Electrical, that's in a battery. Okay. Then we also have a thermocouple. A thermocouple is one where heat energy, of course, you can already see thermal. So when you hear therm, the word therm means heat. So heat energy is being converted to electrical energy. So that's in a thermocouple. Another source will be solar, okay, solar energy, the sunlight. So that is sunlight, where solar energy is being converted to electrical energy. That is in photovoltaic cells, okay? Photovoltaic cell. We are going to deal with this later, okay? We're still going to deal with this later. I already have a video on it though, but I'll still redo it, okay? I'll still make another video to advance it. So we have solar energy is converted to electrical energy. So these are the various sources of direct current. All right, these are the sources of direct current. So we are going to be looking at the chemical electrical source, okay, which is the one we have in what we call electrochemical cells. That's what we call them, batteries. They're called electrochemical cells. Okay, what I'll try to do is I'm going to try and give you the basic working principle of an electrochemical cell. All right, how a battery typically functions, or how a battery typically functions. So we said they are all together called cells. Okay, they are called cells. A cell is just a unit that can provide electrical energy. That's just what a cell is. So, and there are two types of such cell. We have the electrochemical cell, which is a battery, and we also have the electrolytic cell. Let's quickly demystify and differentiate these two. The electrolytic cell is one that uses electrical energy to break down. You can already see that we have lysis here. That's breaking down something. So using electricity. But electrochemical cell is one that uses chemical energy to create electricity. Is that clear? So electrochemical, electrolytic. Okay. So we said this one, there's going to be a conversion from chemical energy to electrical energy. When electrolytic cell, there's going to be a conversion from electrical energy to chemical. So they are reverse of each other, reverse processes of each other. Chemical to electrical energy. But here, electrical energy to chemical energy. Okay, that's the transformation taking place inside them. Now, another thing with the electrochemical cell that differentiates it from the electrolytic cell is that the electrochemical cell actually has, both of them have two electrodes, okay? The cathode and anode. Now, the cathodic cell is in the electrochemical cell, the cathode is the positive. So here, cathode is the positive electrode for an electrochemical cell, while the anode is negative. The anode is the negative electrode. Now, if this concept is not clear to you, you should see the video I'll link in the description of electrochemistry, okay? It's very simple. Now, in electrolytic cell, the cathode is the negative electrode. Cathode is negative, while the anode is positive in electrolytic cell. Don't misplace it. They are just opposite of each other. You can master one already. Okay, so for example, even as a teacher, the one I master to just easily say it. It's not like I don't understand it. Just see my video, you're going to see the full explanation. But to quickly remind myself, I know that electrolysis is the one that has to do with salt and water. So I know that the anode is the one that takes the anions, right? So I know that anode must be positive because anions are negative. That's how I remember it. Then I know if that is the case for this, then the reverse is the case for electrochemical cell. All right. So we said that this one, so the reaction here, so we have, this is the first one. Second difference, the third difference is that in electrochemical cell, the reaction is spontaneous. The reaction is spontaneous. Okay, but in an electrolytic cell, the reaction is non-spontaneous. Non-spontaneous. It is such that non-spontaneous. It is such that there is also Gibbs free energy here, but that is by the way, okay? Gibbs free energy here, just know, Gibbs free energy here is positive, Gibbs free energy here is negative. Gibbs free energy has a negative value, Gibbs free energy has a positive value. For which reason this one is, what's it called now? Spontaneous, this one is non-spontaneous. So if you have a Gibbs free energy that is negative, Okay, let me write that down because now it's becoming relevant because we have to talk about the electrode potential. The electrode potential of the cell here is positive. So remember that Gibbs free energy and electrode potential are opposite of each other, right? The electrode potential here is positive, hence the Gibbs free energy will be negative. Since the Gibbs energy of this place, the change in Gibbs energy is positive, then the change in Gibbs energy here, the electrode potential rather, is standard E cell. Okay, that's what I'm writing. Or just E cell is going to be negative. Is that clear? So those are the major differences between the electrochemical and electrolytic cell. Example of the electrochemical cell is going to be a battery. Okay, it's going to be a battery. And an example of this is going to be any electrolytic cell you can talk about. Any electrolytic cell, right? Now, what is a battery? A battery simply means an aggregation of cells, okay? Many cells coming together, that's a battery, okay? So a battery is a power source, okay? Now, this is the electrical, I'm going to still talk about electrical circuit components, okay? But I just want to quickly separate between battery and cell for you. This is a cell. Then we call it a battery when you see something like this. So it's usually more than one cell that you find in a battery. Exactly. That's just like standard difference, okay? Usually, scientists just, or teachers try to just easily say, use that this is a battery, okay? But you should actually know that there is a slight difference between them. A cell is just one unit, okay? But when there are many units of cells, we call them a battery. Exactly. These already shows the way they are arranged. When we get to circuit components, we're going to talk about that. So, but the point is this. Another way we can draw it is like this. We're going to have this. Okay. I mean, as much as you want, you can maybe have more than one, more than two. Okay. What this shows is that they are being connected together in series. Okay. This also shows it. Now, another thing you should know is that this long arm here is the positive electrode, while this one is the negative terminal. Positive terminal, negative terminal. One of the reasons why they use different this thing is not that the plates are different or different sizes. It's just to show you that one has a higher potential than the other. So this one is of higher potential. Speaking in terms of conventional current, this one has a higher potential than this side. That's the meaning of these two different plates that you have. Okay. Now, so that said, let's get into the types of cell that we have. The types of cell. Now, the types of cell that we have. The first battery was actually invented in 1793 by Alessandro Volta. Alessandro Volta. So that is why the battery the source of the push or drive of current is voltage. Okay, and that is why it is named after Alessandro Volta. Okay, Alessandro Volta. All right, I've talked about him in the introduction to electrostatics, so you should see that video as well so that you can understand his story. All right. Now, like I said, there are two types of cells. We have the primary cell, that is primary electrochemical cell, and the secondary cell. Now, what is the difference between them? You see, a primary cell is one that is non-rechargeable. You can't charge it after use. Okay? But a secondary cell is one that is chargeable after use. So if you have depleted the energy in a primary cell, you can't recharge, you dispose of it, okay? While for a secondary cell, you can recharge and recharge and recharge, okay? The process that recharges the secondary cell is actually electrolytic, okay? It's actually electrolytic. That's why it's the opposite. Do you see that? That's the process that recharges the secondary cell. But primary cell can be used once you're done using. Now you dispose properly. Sometimes they are given back to the, what's it called? You don't just throw them away anyhow. Maybe I'm going to get to that when we discuss the types. All right, let's talk about a simple voltaic cell. Let's talk about a simple voltaic cell. Now, I've mentioned this in the electrochemistry video, but I want to talk about a simple one, a very simple one that is even simpler than the one we used in electrochemistry. So it is also a voltaic cell, okay? It is also a voltaic cell. A voltaic cell uses two electrodes, zinc and copper electrodes, okay? Now, in the electrochemistry video, I probably showed you how both of them can be separated into two different cells. But in this case, I'm going to put them together in one cell, okay? So we're going to have zinc electrode and copper electrode, both immersed in a solution of H2SO4. So there is H2SO4 here, and we're immersing the zinc electrode and the copper electrode. Both of them together are inside the electrolyte. So this, what we have here is our electrolyte. So flying our electrolyte are hydrogen ion, SO4 2 minus ion, and so that's basically it. Then this one here, let it be the zinc electrode, let this one be the copper metal or copper electrode. Do you get the system now? So immediately you connect this system together, something begins to happen. Electricity begins to flow, okay? Now, what are the nitty-gritty to this? What is the thing that happens here? How is electricity being generated? You see, once we immerse this guy, inside the solution of H2SO4, something called electrode potential is developed. There is a potential that is developed here. What is that potential? Potential simply means capacity, right? So the capacity of ion exchange, okay? Ion exchange based on is actually electron that is being exchanged, okay? Such that someone is donating electron and the other is accepting it. So the one that is donating it might either become an ion or become an ion or stop being an ion. Those are the two processes. You can become an ion either by accepting electron or giving electron. Exactly. So that is just what we mean by electrode potential here. That's how to think about it. Exactly. So inside these are flying H pluses and SO4 2 minuses. Now, what happens is this. You remember the electrochemical series? So we have sodium, potassium, sodium, calcium, magnesium, aluminum, iron, lead, okay, so I'm gonna just stop here, right? Because these are the two that I need are already here. So we're gonna see zinc and copper. Now, what do you see here? You're going to see that zinc is higher in this series than copper. So what does that mean? It means that zinc has the capacity to donate electrons and copper will have the capacity to draw electrons. Actually, the electrode potential of a cell is defined by the capacity of the guy that's lower in the electrochemical series to draw electron. Because the pull on electron is what actually drives the process of the working operation of the working principle of an electrochemical cell. It is the pull on electron. So the harder enough the pull on electron is, the higher the possibility of having, the higher the electrode potential. Exactly. The voltage that is generated is dependent on the amount of pull that the other guy has on the electron. So copper here is the one that is going to be accepting the electron. So we say it has a higher reduction potential. Now, reduction potential simply means that capacity to pull electron. Is that clear? So this guy is highly reduced. Why do we know it's reduced? Remember that the definition for reduction is the gain of electrons. So it is the gain of electrons. So because it is gaining electron, we know that it is highly reduced, has a high reduction potential than this guy. So because this guy has a high reduction potential than this guy, so this guy is going to pull electrons from this guy. What that means contextually here is that this zinc will be the one to be donating electron. So zinc metal here will lose electron. So zinc metal will lose electron now and become zinc 2 plus 2e minus. I've taught you this in chemistry before. The way to write how the electron is lost is zinc loses, that's minus, right? 2 electrons. I know that it has valency of 2. That's why I know that it is going to be 2 electrons it will lose. It will lose electron and become zinc 2 plus. But because we don't use minus in chemistry, you carry this guy here and zinc becomes zinc 2 plus. Now, I did more work on this in that video, so do well. I'm going to link in the description. Make sure you watch it. It's going to help you. I just said this so that you can understand one of the problems that cells have. Primary cells, especially, they have a particular problem. Now, what happens is this. Once this guy loses the electron, it forms zinc ion inside the solution, right? Of course, this guy will also accept the electron. These guys will be, hydrogens will be the one to accept the electrons. So when the hydrogen accepts electron, hydrogen can accept one electron, but there are two electrons being donated. So it means that two hydrogens accept two electrons and they become what? Hydrogen gases. Exactly. So this process is this is going to be loss of electrons, so it's called reduction, and this process is oxidation. Exactly. So the hydrogens are being oxidized and they are leaving the solution as gases. Exactly. So they are going to lose this solution, leave this solution as gases. Keep that in mind. Now, this is where the problem now begins. Immediately, the hydrogens begin to gain the electron. Now, they are going to form hydrogen bubbles. Now listen, you know that the electrons are being released here and they are coming into this place. Since the electrons are being released and they are coming into this place, then we know that the hydrogens, they are going to cluster at the base of this copper. They are going to come and hug the copper. That's pretty much what they're doing. They're going to hug the copper, or gather themselves at the copper electrodes. Okay? Now, when that happens, the process known as polarization occurs. Something called polarization has occurred. Now, what is polarization? Here, this is the first problem that primary cells have, polarization. And that is why it doesn't run for so long, okay? Polarization is the process where these hydrogen bubbles form at the base of this electrode. Now, this copper electrode, now, because the hydrogen bubbles form at the base of this guy, now I'm going to reiterate that, because the copper, these hydrogen gases form at the base of this guy, they are going to, set up what is called a back EMF. They'll set up what? A back EMF that opposes the direction of the flow of current, that opposes the EMF that was already or initially set up. I'm going to repeat that. I said that the hydrogen electrons are going to cluster at the base of this guy, and they're going to set up a back EMF. An EMF that opposes, EMF simply means electromotive force, okay? And I'm going to explain that in detail. Electromotive force is just like voltage. It's also voltage, okay? Another way to talk about voltage. There are two major ways to talk about voltage. We have EMF and potential difference, and I'm going to separate between the two for you, okay? Now, we use EMF here because it is within the cell, not potential difference. Potential difference is the voltage across a particular component of the circuit. But EMF is the voltage of the cell. So because we are referencing the cell right now, we are going to be using EMF. So it sets up a back EMF that opposes the direction of the flow of the initial flow of current. Exactly. So what did we say will happen? We said that this zinc is going to lose electron. So once it loses electron, the zinc will join solution, electrons will climb here. Are you seeing the direction of electrons now? Electrons will come here. Okay, so two electrons are moving. They will enter this place. So because of that reason, negative charges, hydrogen ion, positively charged, they come here because in electrostatics we already learned that positive and negative attract. So they come here, they come and cluster here to just get oxidized. It's not their fault, okay? So they want to get oxidized. On oxidization, they are going to become gases and they will leave the solution. But the problem is that some of them, they get so much that some of them do not leave. They actually cluster at the base of this guy. And by clustering there, they set up an EMF. Now, listen, why is it called back EMF? The original position, the original movement of electrons is from here to this place. So what happens is this. You see that so the original position of electron is supposed to be like this, right? In this direction, That's the original path of the electrons. When hydrogen ions cluster here, they set up a back EMF. Okay? Now, why do they set up a back EMF? If you look at hydrogen and copper here, you see that hydrogen is a little bit more electropositive than copper. Look at it. Copper is higher in the series, meaning that hydrogen is higher in the series, meaning that copper is still going to have a higher electrode potential or a higher reduction potential than hydrogen, meaning that copper, if you connect copper and hydrogen together, copper will be the one to still draw electron, hydrogen will be the one to still donate electron. So what happens is that because hydrogen gases are beginning to cluster around here, what will happen is that this copper will begin to now draw electrons in the opposite direction. That's why it's called a back EMF. Is that clear? Now, what is the solution to polarization? The solution to polarization is that a depolarizer is used. That's the typical, that's the most common exam question, okay? A depolarizer is used. There are different depolarizers. In the Leclanche cell, the depolarizer is manganese 4 oxide, MnO2, depolarizer. And for Daniel cell does not even use depolarizer because copper sulfate, which is one of his electrolytes, is already the polarizing agent. So hydrogen bubbles do not set up. Exactly. Hydrogen bubbles, they don't set up at the copper electrode. So that is the advantage of Daniel cell over Leclanche cell. But in Leclanche cell, we need a depolarizer like manganese 4 oxide to stop back EMF or polarization from occurring. Now, the next thing we want to talk about is the second problem. So this is the first problem. The second problem is local action. Now, what is local action? Local action is basically referring to local action is a consequence of the nature of the electrode. Okay, so for example, in zinc, you see, commercial zinc are not 100% pure. Commercially generated or commercially refined zinc, they are commercially, what's it called? Is it refined? I don't know. The zinc that is obtained, okay, commercially, that we process commercially, is not 100% pure. It means that there will still be impurities like iron, okay, like calcium, blah blah blah. All those guys, some metals will still be embedded within that zinc metal. So because those guys are within the zinc metal, local action is a problem that occurs when the cell is not even in use at all. Polarization is when the cell is in use. But you see, when the cell is not in use, this zinc electrode, what will happen is that the impurities within it are going to set up an internal voltage. They will set up an internal EMF such that they will begin to now exchange electrons with the zinc. Okay, so because of that internal EMF that is set up, this whole system will not run for long, because before you know it, zinc would have depleted the electron, and by the time you want to use it, it has discharged. So that's basically like discharging. That's what is called local action. The battery discharges itself. Why? Because this zinc guy is actually losing electron. This zinc guy is impure. It has metals within it, impurities that will cause it to be depolarized, that will cause it to be, losing its own electron, even while the system is not running. The system is not in use at all. Exactly. So that is that with local action. Now, what is the solution to local action? The solution is amalgamation. Amalgamation. I said this one is depolarization. The next one is the solution to this one is amalgamation. Now, if you remember, the word amalgam simply refers to using mercury and something. That's going to form an amalgam. Okay? Amalgamation simply means coming together. That's the meaning of the word. But in chemistry, when you use amalgam, it's usually mercury plus something. Just remember that. So in this case, amalgamation, what we do is basically that zinc metal, when it is not in use, it is rubbed with mercury. So you cover it with mercury or coat it with mercury. So by coating with mercury will prevent internal EMF to be set up by the time the cell is not in use. Is that clear? All right. So we've talked about the types of primary cell. Examples of primary cell that we have. We have the Leclanche cell, like I said, Leclanche cell, Daniel cell, which other one? Daniel cell. Okay. That's very okay. There's also there's also level of superiority in terms of how much they deliver. There's something called one of the most efficient primary cell is the lithium organic and lithium inorganic cell. Okay, now it has high delivery rate, that is, it is very efficient in terms of how much power it can generate, and doesn't get used up easily. Okay, so that's primarily it. That's primarily it. So there are other examples, but these are the ones you are most likely going to come across in your exam. So, and there are two types of Leclanché cell. We have the dry Leclanché cell and the wet Leclanché cell. This thing, how is it moving? Don't move. Uh-huh. So we have the dry Leclanché cell and the wet Leclanché cell. It's not capturing already. Let me open one. All right, so let's move to secondary cells now. Now you see, for secondary cells, we have what is a secondary cell first? Cells that are rechargeable after use. Now, and I told you that the process that recharges secondary cell is just electrolytic process, which is opposite of electrochemical cell. Now, examples of secondary cells are, this order I want to list them is the order of their efficiency also. We have the example of secondary cells. So we have cell, let me just clean this part. So examples of secondary cells. We have the lead acid accumulator. The lead acid is the most common one, most commonly used secondary cell. We also have the lead lead acid, lead cadmium, cadmium? Silver cadmium, sorry. The silver cadmium is the most efficient. Silver cadmium. Then we have nicad. Okay, yes. Nickel cadmium. Yes, that's what I want to remember. The nickel cadmium. So the take home from this is just the level of efficiency. This is the most efficient. So we have the silver cadmium being the most efficient, and we have the silver carbon also. Yeah. No, nickel silver. No, Ag, that's nickel silver now. Or silver nickel. I've forgotten the arrangement. I just know that this is the most efficient and this is the most common. Okay, most efficient because it is delivers higher voltage, quicker charge time. Okay, it can be charged quickly than the rest of them, recharge quickly than the rest of them. So that's primarily what you should know about these cells. Now let's talk about the electric circuit. The electric circuit. So what is the electric circuit? Now what is an electric circuit? Now, please, this is my number that I put here. Is for you to contact me for if you have questions, you have studied a particular topic in JAM for physics or maths or chemistry or physics, and you need good questions. Okay, I have a bank of very good questions that you can ask me to give to you. That's my WhatsApp number. Then, of course, for those of you that are writing maths in JAM, there's a very good textbook that I have been, I just didn't come with it, that I've been advertising. Okay, so just reach out to me. I'll send you the number of the author, and you communicate with him. You can, you buy it from him. But it's a very good textbook. Okay, very, very good textbook. I like that you have it. I also have my own copy. So, electric circuit. Now, electric circuit is basically the path, or a circuit is basically the path. Okay, we call it electric circuit. Electric circuit is the path provided for current to flow. Path for current to flow, or the path through which current flows. That is what an electric circuit is. Now, electric circuit has various components. Electric circuit has various components. Before we talk about electric circuit, let's talk about the types of circuit. No, let's first talk about the components. What makes up a circuit? Okay, the components include the source. All right, the power source. Usually a battery or just any source. So if it is just any source, this one refers to whether it is AC or DC. You can just use this. If the power source could be anything, not necessarily a battery if you see it like this. But if it's like this, definitely know that it is a battery. Okay? It's a battery. So, but that loop, that complete loop is what you call a circuit, okay? So the source is where the power source, where the power or the push on electron is coming from. That's the source, okay? It's usually called the voltage source, okay? That's the voltage source because the push or pull on electron is because of the voltage, okay? In which case we are soon going to begin to call potential difference as soon as we understand, we get into it now. So I said that the power source is one of the major components. The other is the load. The load. Now, the load might come in different forms. There are many components that might make up the load or what the power is driving. That's basically what we call the load, okay? What the power is driving. Then there is the switch. There is the switch. Now, the switch is a very important component. It's the one that actually connects, it continues the circuit or discontinues it. So, for example, I'm going to draw what they look like for you, okay? I'm going to draw it. Now, for the load, we have the resistor. Now, the resistor is the component that provides resistance to the flow of current. Now, why is resistance necessary for the flow of current? Now, the amount of current that comes into a particular component of the circuit is very important, okay? So there are some components that don't require huge current. So to reduce the amount of current that will enter that place, you can use the resistance to resist some current so that not all current will flow across. Is that clear? So that's one of the use of the resistance. The resistor, okay? Resistor is a component. A capacitor is a component, okay? So basically, resistor offers opposition to the flow of current. A capacitor basically stores charge, okay? I have dealt with this in electrostatics. So this one basically stores charge. I'm going to show you when I draw circuit components and their symbols. The symbol. So it consists of two parallel plates, okay? That's the typical representation. So that's just a capacitor for you. Then, let me take water. We have capacitor. I think we also have an inductor. We also have an inductor. An inductor is, this one stores electric charge, stores electrical energy, stores electric charge as electrical energy. Stores how is it called? Capacitor stores electrical charge, okay? While in capacitors, they store charge in electric field. That's what I wanted to remember. They store electric charge in electric field. But inductors stores electric charge. They also store electric charge, but in a magnetic field. So that's the difference, okay? In a magnetic field. I'm going to tell you what the different ways of the very unique or the very profound use that these two components are found in electricity. So we also have other components like the diode, the LED, light emitting diode, LDR, transistors, all those other components. They are connected to a circuit. And of course the switch, or there's also a fuse, okay? There's also a fuse, right? So now let's draw the circuit component, the component of circuits, and their symbols. How do you recognize that this is which in a circuit? So now, let's begin with a switch. A switch basically looks like this in a circuit. A switch looks like this in a circuit. So for this one, you'll see that these two edges are not touching. So that's an open switch. A switch is also called a key, okay? So if it is closed, I mean, that's why it's called a key, okay? It is the key to unlocking the power of the circuit. Makes sense? So of course, if it is closed, that is when current can run, okay? So the way you connect it is simply like this. So I'm going to put my key here, okay? So if I have something like this, all right, current is not running, current cannot run. But once it is closed, if I have it this way, it is closed. Current can pass through, current can flow. Okay, so this is a working circuit. If it's open, it's not a working circuit. Now, the next one is a resistor. Now, a resistor, no, a power source, a power source. The power source can look in two ways. You could have a cell, or like I said, a battery that will look like this. Now, it could also look this way, okay, depending on whether it is DC or AC. Now, you could also have a power source like this. This one is AC circuit, AC power source, AC power source. Now, another one is, now let's talk about the resistor. The resistor looks like this. You see, what I plan to do in this video is to cover all the basic things that you must know. You can't say you know electricity without knowing all these basic things, okay? Before we now deal with the, in-depth stuff. So resistor pretty much looks like this. Then we have a capacitor, which I said stores electric charge in an electric field. Don't forget. It looks like this. It is a parallel plate. You're going to see that the plates are different from the plates of a voltage source, the power source. This one have parallel plates, and that's one example of capacitors. When we deal with, when we now do the A-level, I think I've also covered that before, the kind of capacitors that we have. So this one is a parallel plate capacitor, and that's the typical capacitor that we use, the most common types of capacitor. Then the next one is an inductor. Now an inductor, basically we said, stores electric charge in a magnetic field. It looks like this. Now, keep in mind that it is different from resistor, okay? Resistor has zigzag lines. This one has squiggly, like, I don't know, what do they call that thing? Squiggly looking line, like spring, okay? So that's an inductor, all right. It basically works like by having, there is also an iron core within it, okay? No. The inductor is basically the coil. The inductor is the coil. There is also a transformer. There's also a component. There's a transformer. Now this one basically steps up or steps down electric circuit, okay? So, and that one looks like this. Now then there is a plate here. Okay, now what does this show? This shows you that there's going to be an iron core in between them, around which that coil will be wound, and then there's also a distance of separation. So basically, this one, if these were to look like this, such that this one, which is the inlet, this one is the outlet, this one that comes in, you see that the coils are more than the one that is going out. This kind of transformer will be called a step-down transformer. The step-down transformer is the one that we use in our houses because the amount of voltage that comes from the source is very high, and our home appliances uses less than 220 volts. And the supply is as much as 33,000 volts. So it has to be stepped down, otherwise it's going to destroy our circuit, our appliances. So this guy steps it down, from what you can see. If the coil of this side is higher than the coil of this side, then that's a step up, basically increasing the voltage. That's what a transformer does. In this one we say step down, it means that if the voltage coming in here is high, it steps it down, makes it lower. If it's a step up transformer, the voltage coming in is low, it increases it. The diagram is pretty much the same, only that the other side we will have more coils, more turns on the guy. Then we have the diode. A diode looks like this. Now a diode is basically a component that allows current to flow in one direction. It allows component to flow in one direction. That direction is called the forward bias direction. I've covered this in a 5 days of physics video. Do well to see that last video, okay? But of course, I'll still cover its basic electronics. I'm going to cover it again. But I'll now deal with semiconductors a lot, where I'm going to deal with how a diode is formed, how it works, its operation. But just know that this guy works in the forward bias direction, and I said that this direction, you can see the arrow. That's what it means. This arrow is actually showing the only direction in which current can flow. What that means is that if you were to connect the battery the wrong way to this system, for example, you connect the battery this way, current will not flow, because this shows that, remember, I said that, did I say it? I can't remember if I said it. Conventional current flows in the circuit from positive to negative. Just know that. Conventional current flows from positive to negative. Meaning that if you connect your component like this, your battery this way, current will not flow across this diode. Yes, current will not flow across this diode. Why? Because this one blocks it. That's what this wall means. It's like a wall, okay? But if you were to connect it this way, then it means current is going to flow in this direction, so it's going to allow current to flow like this, and that is the forward bias. It doesn't allow the backward bias. Make sense? All right. So that is what a diode is, a one-way, unidirectional, whatever, and that's why it can be used as it can be used for converting AC to DC. You can already tell the use now from the way it works, because it allows current to flow in just one direction. So because of that, it can be used to convert current that is flowing in two directions initially. You use it to make it flow in one direction. That's one of the functions of a diode. There's a special type of diode that is called the LED. It means light emitting diode. Light emitting diode. Okay, it's basically a diode still, but the thing with this one is that there's a cycle here, and then you now see some two arrows go like drawn. That's the circuit representation, okay? You see two arrows going like that to show that light is being emitted, okay? The light is being emitted. And there are two types of resistor. There is the variable resistor and there is the fixed resistor. This one you are seeing here, these two here, are the fixed resistor. The variable resistor looks like this. The variable resistor looks like this. The variable resistor will look, and this one is, I think, like this. Okay, that's the variable resistor. But the thermistor looks how? I'm sorry. Okay, but that's basically it. I'm gonna remember when we start to draw circuits. Now this is when I'm supposed to remember. The variable resistor looks like this. The thermistor, they look alike. Okay, that's why I can't really remember. Let's deal with the other components. There's also something called a two-way switch, okay? There's a two-way switch. You could have what looks like this. This one is a two-way switch, okay? That's because you can see already two ways. Right. Then there is, when you see this, it means it's a junction where wires are joined. That's just it means, it's a junction. Then these other components, there are many other components I have not covered though. I don't know why I can't remember right now. There's also the light dependent resistor. Okay, that's what it looks like. I think this is in cycle, yes. So this one shows that light is incident on it, okay? That's the meaning of light, LDR, light dependent resistor, okay? Which other one have I not covered? That thermistor resistor thing. I think thermistor is going to look like this. Yeah. Thermistor. thermistor. A thermistor is a non-ohmic conductor. So resistance reduces as voltage increases, as current increases also. Or as resistance increases, current increases. It's a non-ohmic conductor. I think this is thermistor and this one is variable resistor. Alright, so that said on voltage sources. Now, if you have not been listening since, make sure to listen now because we want to really start the aspect that deals with calculation now. The aspect that deals with calculation. Now, you see these first three that we mentioned, the power source, that's voltage, the resistance and resistor and all. Those are the ones, those first three or four are the ones that we mostly deal with in our circuit, okay? In our circuit analysis. So, okay. So I now said, let's now talk about what is called current, okay? No, types of circuit. Let's go deal with types of circuit. I didn't cover that because it is very essential, okay? We have the open circuit, the closed circuit, and the short circuit. An open circuit is a circuit that the key or the switch is closed. I mean, an open circuit is the one in which the key or switch is open, for which reason current does not flow, okay? So the key is open, so this is an open circuit. This is an open circuit. Current does not flow, so that's an open circuit. A closed circuit is one in which the key is closed, hence current is flowing. As you can in that instance, the current is flowing. Then a short circuit is one in which, due to wrong connection, usually, another path, an alternative path is provided for current to flow. So, for example, it will be a closed circuit, okay? Even in a closed state, current will not flow across the load. Keep in mind that this is more, so this is a closed, this, for example, is a short circuit. Why? You can already see that there's an alternative path here that's provided for current to flow. And current does not like to do what? Current does not like the load. So rather than go across the load, it will rather go across the free path and come here. Do you understand? So the current will come back here and like that. So because of this, we call it a short circuit. A short circuit, which is one in which current does not flow across the road because an alternative path has been created for current to flow. Hence, the load does not get powered or get very low power. Exactly. So those are the three types of circuit. Now let's now talk about current. Now what is current? Current, we said, is the rate of flow of charge. Current is given by I, given by I, is the rate of flow of charge, time rate of flow of charge. Now, in my previous video, I've derived how this is the expression for current microscopically, okay? So do well to see that video. I'll also link it in the description. Current is the rate of flow of charge. Now, what do we have to talk about in current? Okay, what current is measured in, so it means that current is measured in, denoted by I and measured in amperes, okay? Amperes, all right? So, and, or amp, okay, denoted by A, is denoted by A, and it is measured in amps with an ammeter. Don't forget that, an ammeter. That's the device. This is the device. This is the unit. Is that clear? This is the symbol. All right, and this is the symbol for the unit. All right, measured with an ammeter. Now, when you connect an ammeter in a circuit, this is the symbol for an ammeter. You see, I didn't cover those ones. This one is called an ammeter. This is what is called an ammeter. It looks like this. Very simple. Okay, so when you connect an ammeter, it should be connected in series to the circuit. What does series connection mean? There are two connections for a circuit. There is a parallel connection and there is a serial connection, or we say series connection. In parallel connection, the components will be connected across. Okay? So for example, let me first deal with series because I'm dealing with current now. So an ammeter, for example, I said we use ammeter to measure the amount of current in the circuit. So how do we connect it? If this is my load and this is my source, I'll now connect an ammeter like this. So do you see? So I'm connecting an ammeter in series. Series means following each other on the same line. That's the meaning of series. Okay? Ever feel the leaflet and you see serial number? Serial number means we are following each other, one after the other, step by step. So that's the way it is. This one, this component is just following this component. This is the same length of wire that's going like this. There's no change in the wire, okay? It's the same length of wire that is going like this. So you can already see an ammeter is connected in series, okay, to the circuit. All right. So that's series connection. But of course, you see that's a dial, okay? It is calibrated. Okay, so this point could be the 0 amperes, let's say 5 amperes, 10 amperes, 20 amperes. Let's say the maximum it can measure is 20 amperes. Now, what happens is this: if you connect an ammeter and the ammeter deflects away from the zero mark, you should change the connection because it's supposed to deflect in this direction. So it means you have put the negative into positive and you have misconnected it. That's the meaning. Is that clear? I repeat myself. When you connect it, you are going to see two knobs here. You connect your wire here, your wire here. If you connect it and the indicator or detector actually moves away from zero in this direction, then you should change the connection of the wire. You see that it will now deflect in the right direction so that the calibration can be read. Is that clear? So that is for an ammeter. And an ammeter generally has low resistance. Okay? It has very low resistance such that it doesn't add to the resistance on the current. Okay, because the load already has a resistance. The conductor already has resistance. So the ammeter is typically designed to have very low resistance as much as microamperes. So that's a low resistance and that's an ammeter. So that's basically for an ammeter. Now, the principle of operation of we deal with current based using Ohm's law. Okay, but before we deal with Ohm's law, I'd like us to first deal with voltage. Okay, let's quickly talk about voltage. Now, what is voltage? Now, voltage is expressed discussed with two expressions. We have the EMF and we have potential difference. We have the EMF and the potential difference. You see, EMF simply means electromotive force. I guess you should already know that. Electromotive force. All right. Now, what does this one mean? Electromotive force is the total voltage that the cell can deliver, that a battery can deliver, for example, can deliver. That's the EMF of the cell. So when you are talking about a cell, you use the term EMF. You will not say the potential difference of the battery. Exactly. You say the EMF of the battery or the EMF of the cell. But what is potential difference? It's still voltage, it's still measured voltage, but the potential difference is basically the amount of voltage that will pass across a particular load or a particular electrical component. That is potential difference, for example, across this resistor. When the voltage across the resistor will be called potential difference because it measures difference in potential from one end of the circuit, from one end of the device of the components to the other. The difference in the voltage, whether voltage dropped or voltage increased. Is that clear? So that is what it does. That's why we call it. We use the word potential difference when it has to do with a circuit component, except from a battery or a cell, in which case we use an EMF. Is that clear? Good. So what is voltage? We said voltage is basically the push on the electrons. Voltage is the push, the amount of push on the electron. So you typically should know that a 5-volt battery is going to deliver more push than a 3-volt battery. That's basically it. Now, how do we now connect? What's the diagram? No, let's first talk about what is used to measure it. Now it is measured using a voltmeter, a volt or voltameter. That's another way to to call it. But we call it voltmeter typically. A voltmeter has the symbol V also. Okay, that's the symbol for voltage to V. Now, a voltmeter also has two terminals, typically like this too. If you connect it and it reads away from the zero mark in the opposite direction where there is no calibration, change the wire the same way like we talked about in this one. But the point is now is that for voltmeter, you don't connect. You remember how we say we connect this guy? This guy connect an ammeter in series, but this guy you connect in parallel, and I'm going to explain why. So this is our resistor. Okay, this is our resistor, and what we want to do is we want to measure the voltage across it. The voltage across this resistor. The way to measure it is to put a voltmeter. This is the symbol for a voltmeter. You put a voltmeter across it, and you can already see, right? So a voltmeter goes across it. Now, why you have to measure it, put it that way? Because the voltmeter measures the potential difference. You now get it now. The potential difference across these two ends of the conductor. What it does is basically subtract the voltage entering here from the voltage going out of here. Okay? So, voltage going out from voltage entering, that's basically it. Once you subtract it, then is the value that it will reach. So that's how to connect the voltmeter across the component. Is that clear? All right. So that's for voltage. Now, how do we now connect cells together? How do we connect cells? You have two types of arrangement. We have the series arrangement, like I said, and the parallel arrangement. Now, let's connect in series. That's the correct way to connect a battery, though. For example, if I have a 2-volt battery, let's say I have a 2-volt battery. This way to connect them. I'll connect the first battery like this. I'm going to draw the typical diagram. Here's a battery. It looks like this. To another battery like this. To another battery that looks like this. Now keep in mind, if your battery looks like this end could be called the positive and this end the negative. So what I am doing is basically this negative is here, positive, negative, positive, negative, positive. So what am I doing? I'm connecting positive to negative, negative, positive to negative, positive, negative, and positive to negative, positive to negative, positive. That's where we connect the voltage. We connect cells. And with that, if all of them are 2 volts, 2 volts, 2 volts, what will happen is that we're going to get altogether the total power, the total EMF that will be delivered in an ideal case is 6 volts. Now keep in mind the word ideal. I'll soon talk about that. Now, series is 2 volts, 2 volts, 2 volts for this guy, so we got 6 volts. So the way we draw that in circuit diagram is we'll not be drawing battery. See, it took my time. What we'll basically do is like this. It's like this. So if all of them are 2 volts, 2 volts, there are 3 2 volts here, that's 6 volts, all right? But what if you now connect like this? What if you connect them like this? Watch. Both of them, they are 2 volts, and you now connect them like this. What kind of connection is this? This is positive terminal, negative terminal, positive. So you are seeing that you are connecting here, you are connecting a negative to negative, and that is going to basically reverse the direction of flow. If both of them are 2 volts, 2 volts, what will happen is that the amount of voltage that will be delivered is 0 volts. Why? Because the voltages are going to flow in different directions, hence they cancel out. So because of that, you're going to have 0 volts, no current moving in the circuit. But what if you now connect a 5-volt battery and a 5-volt battery and a 7-volt battery? If you connect a 5-volt battery and a 7-volt battery, now you have to determine the direction of flow here and how much voltage will flow. So looking here, you will know that this one wants to deliver current in this direction. This one wants to deliver current in this direction. So what will happen is that the currents will cancel out, some currents will cancel out, then 2 volts is the amount of voltage that will run. But in which direction? The voltage is going to run in the direction of the more powerful battery. Exactly. The voltage will run in the direction of the more powerful battery. So it's going to flow like this. Exactly. It's going to flow like this. All right. Now, keep in mind that when you connect cells of equal voltage. Connect cells of equal voltage. What if you were to now and connect them in series? What if you now want to connect in parallel? What's the implication? Here's the implication. If you connect batteries or cells of the same voltage, if you connect them in parallel, like you can see, parallel simply means across each other like this. If you connect them in parallel, here's what will happen. If I have 2 volts here and 2 volts here, the amount of voltage that will be delivered is still 2 volts in an ideal case. Still 2 volts. Okay? Why am I mentioning ideal? This is it. Cells don't deliver exactly their rating. Do you understand? Because there's something called internal resistance, which we'll get to. This one I'm not talking about it yet is because I've not talked about resistance. And that's where we are going to capture our whatever we're doing and solve calculations. Okay? So, but this knowledge is necessary for solving calculation. So 2 volts is the amount of voltage that it will deliver. For it to deliver the 4 volts you're intending, connect them in series. Exactly. What if you now connect them this way? Now look at it. Positive, negative here. Negative, positive here. Once you connect it this way, no current will flow. Exactly. Current will not flow. And of course, if you connect in parallel, so you use different guys, no current will still flow. So that's the case with voltage. Now, the other thing to talk about with voltage is we've talked about EMF, right? The total EMF. Now, okay, let me quickly talk about something. So there is EMF. The EMF is going to be the voltage that flows out, okay, of the voltage that this guy is rated to deliver. That is the EMF. Potential difference is the voltage that flows out, that flows across here. Exactly, that's potential difference. I'm trying not to miss any information, okay? That's for voltage. Let's go to resistance. Maybe there's something more I can remember. Now, resistance is just opposition to flow of current. Resistance is what? Opposition to the flow of current. I hope these people look. Okay. So resistance is the opposition to the flow of current. Now, what does opposition to the flow of current mean? It means that there's an hindrance to the flow of current. And I've told you what we use it for. Some circuitry components might not require an amount of current that is being delivered. So you use resistance to oppose the current flowing such that that current does not get to that component of the circuit, so that that component of the circuit will not get spoiled. All right. So that's resistance. Now there's something about resistance that you have to know. There are 2 types of resistance. We have the internal resistance and the external resistance. The internal resistance is denoted by small r, external resistance is denoted by capital R. Okay? Now, internal resistance is just the resistance within the cell. So this is it. No cell is 100% efficient. So our battery, for example, is not going to be 100% efficient. If it's rated to deliver 6 volts, it may deliver 5.6, 5.7, 5.8 for very efficient one, 5.9. Okay, so it means that if it's 5.9 that is delivering, and it is rated to deliver 6, it means that some of those voltage, some of the 6 volts has been lost, which is 1 volt. Okay, so that 1 volt that it lost was lost due to the internal resistance. So it means that there is some voltage that is lost here, right? Some voltage was lost in this place, and that voltage will be due to what? Internal resistance. This is where something called Ohm's law now comes in. Okay, Ohm's law, named after George Ohm. George Ohm. Now, Ohm's law states that the current, I have derived the equation before, so I'll link the video in the description. Ohm's law says that the voltage across a metallic conductor is directly proportional to the current flowing through it. given that the resistance or the temperature and other physical conditions are constant. So we know that V is equal to IR. That's the relationship between them. I always teach my students with a formula triangle. Just draw this. Draw T inside a triangle. Put V here, put I here, R. V equal to IR. So to find current, just cover current with V over R. To find resistance, cover resistance with V over I. To find voltage, cover voltage with I times R. Is that clear? Good. So that is the formula. Now, I now said that. So to now calculate the voltage that is lost inside here, since voltage is equal to I times R, then this will be V equal to I R. Keep in mind that the I is capital and R is small. The external resistance is the resistance that is delivered, the resistance that is given to the flow of current in the external circuit. So this place is the internal circuit, this place, from this negative plate to this positive plate. That's the external circuit, internal circuit. The external circuit is going to be the current, the external circuit is this outside, from here to here. That's the external circuit. So the voltage, let's call this one VI or V1. Then V2 will be the external resistance, the voltage loss in the external circuit, because there's going to be voltage loss here. Okay, the voltage loss, one of what happens is that voltage is lost because electrical energy is being converted to heat energy. That's why you see some of these electric components that have resistance, they heat up. Okay, they heat up because they are converting electrical energy to heat energy. So V2 will become the I times R. Keep in mind that these I and I are the same. Why? Because you can see that they are in series. So when you connect components in series, when you connect resistors in series, for example, I'm going to still talk about the connection. Okay, the current flowing through them is the same. I will expatiate that soon. So the total EMF is going to be V1 plus V2. Okay, EMF we denote by E sometimes. So E will be equal to I small r plus I big R. But given that the currents are the same, then we know that E is going to be I into bracket R plus R. So this is how to calculate the total EMF in the circuit. That's how to calculate the total EMF in the circuit, excuse me. So that is EMF. So why is there internal resistance? I said the battery is not 100% efficient. In real life, it always delivers less, a little less at least, for very good batteries, a little less than the rating. Is that clear? So some voltage will be lost. So in order to be absolute in your calculation, you have to calculate the lost voltage. This one is the lost voltage in the internal resistance due to internal resistance, and this one is lost voltage due to external resistance. All right. Now let's talk about what do you use to, measure the resistance of a resistor. The resistance of a resistor is measured in ohms. Resistance is measured in what? Ohms. Okay. And that ohms is dependent on the intrinsic nature of the material itself. So all conductors have a measure of resistance. Okay. All conductors have a measure of resistance known as resistivity. Okay. So from the mathematical equation that I derived for you, that I will link in the description, I don't want to get into it again. I'll link in the description. I already showed you that how that R is equal to rho L over A. So this shows us that the resistance, where R is resistance, the resistance is directly proportional to the length of that conductor, meaning that the longer the conductor, the higher the resistance. And the same resistance is inversely proportional to the area of the conductor, meaning that the wider the conductor, the less the resistance that it poses. So, and the resistivity is the constant, okay? It's a constant for every material, okay? Now, there is something called conductivity as well. Conductivity versus resistivity. Resistivity is ohms, this one is sigma. So, see, the conductivity is how much a conductor allows electricity to pass through it. Okay, the resistivity is directly proportional, is inversely proportional to the conductivity of a conductor. So meaning that the higher the conductivity, if the conductivity is high, if the relationship between them is inverse. Okay, let me repeat that. The relationship between them is inverse. Meaning that if the resistivity is high, the conductivity will be low. If the resistivity is low, the conductivity will be high. Is that clear? That is the relationship between them. And of course, you can already see this relationship. So we know that rho is equal to 1 over sigma, such that if I say that the resistivity of a material is blah, 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 find the conductivity. Simply use this equation. Is that clear? Good. Good. So this said, let's solve one question. If a question says that a wire, a metallic conductor, a wire of length 15 centimeters and 15 centimeters and diameter 3 centimeters has a resistivity of 2.0 times 10 to the power minus 3 ohms meters. Okay, find the resistance, for example, and B, the resistivity is already given. Let's find the conductivity. Conductivity. Very simple question. How do you solve this question? So basically, the length of the wire is given. So length is 1.15 centimeter. So 15 centimeter, you convert to meters, that becomes 0.15 meters. Make sure to convert. Okay. Then the length, the diameter is 3 centimeters. That is 0.03 meters. But we don't need diameter in our formula. Remember that R, okay, we're also giving resistivity. Let's write that first. 2.0 times 10 to the power minus 3 ohms meter. Now listen. The diameter is given, and the formula is that resistance is directly proportional to air, inverse proportional to area, and then you have your constant rho like that. Now this rho is given, length is given, but area is not given. It's the diameter that is given. So, and a wire looks pretty much, the cross section of the wire is cyclical. So because it has a cyclic cross section, it means that to find the area, you use the area of a cycle. So area of a cycle is going to be pi r squared. And you can use diameter directly to calculate. Your formula will become pi d squared over 4, I think, because r is equal to d over 2. So if you substitute d over 2 here, square that, and square it is 4. So let's use this directly. Because of lack of calculator or for the want of calculator, I'm going to retain pi in my own calculation. I hope you forgive me. R is going to be, we're calculating A. Area is going to be pi times D. What's our D? 0.03 all squared over 4. So A becomes pi dot 3 times 10 to the power minus 2 all squared over 4. 3 squared 9. So area becomes 3 squared 9 over 4 times 10 to the power minus 4. So 4 in that is 2.1 over 4, that's 2.25. 2.25 times 10 to the power minus 4 meter squared, that's the area. So we now plug into the formula, resistance is equal to ohms, rho is 2 times 10 to the power minus 3 ohms meter times length. What's the length of the wire? 0.15 over, what is the area? Area of the wire, 2.25 times 10 to the power minus 4. I hope we'll not need a calculator here. Let's try. R equal to, what am I calculating? There's pi. So don't forget there's pi because we didn't use pi here. Alright? So this has pi. So from here, I know that 2 times this will give me 0.3. Yes, this will give me 0.3. So I can say, or how should we do it? See, this guy can cut this guy. So let's do something with this. We can say, we can move this guy. We can say 2 times 0.15, 2 times 15 times 10 to the power minus 2, times 10 to the power minus 3. That will be times 10 to the power minus 5 at the top. Over, this one will become 225 times 10 to the power minus 6 pi. You just use your calculator if you don't understand the manipulation I did here. This takes care of this, this takes care of this. This guy gives 15. 2 here 1, 2 here 7.5. Or should we do it that way? No. 7.5. That's 15 over 2. Let's do it as 15 over 2. So 1 over 15 over 2 is 2 over 15. So that becomes 2 over 15 times 10 raised to the power minus 5 minus this, that's plus 6. So that becomes 2 over 5, 2 over 15 times 10 raised to the power 1, that's times 10. 2 divided by 15, that's 0.13. 0.13 times 10 raised to the power 1. So that becomes 1.3. That's the answer. 1.3 pi. Remember that there is pi. Oh, our calculation is erroneous because there is pi here. So what you should do is put the answer in the comment section, please. Just do 2 over 15 pi times 10 raised to the power minus 5 times 10 to the power 1. So do this. 2 divided by 15 pi times 10 raised to the power 1. Put the answer in the comment section. The answer will be whatever you have, ohms. Then B now says we can't calculate B because we are within. Okay, this one is conductivity. Okay. So conductivity is 1 over resistivity. From this, you know, resistivity is 1 over conductivity. So conductivity is 1 over resistivity. So this becomes 1 over, what is conductivity? Resistivity. Resistivity is given by 2 times 10 to the power minus 3. That becomes 1 over 2 times 1 over this means 10 to the power minus 3. I hope you believe that. Good. 10 to the power 3 rather, because minus, okay, plus. So that will be 0.5 times 10 to the power 3. That becomes 5 times 10 to the power 2. That's 500. 500. Now, this guy is ohms meter. Resistivity is ohms meter, right? Meter. R A over L. So that will be ohms meter squared. So that's ohm meter. So it means conductivity will be inverse ohms meter. Sorry, where is it? The answer will be this ohms meter per ohms meter. Is that clear? So that is it for resistance and all. Now let's now deal with circuits. We're going to solve like 2 questions and that will be the end of the video. Let me see how many minutes. Oh, now. Okay. I hope you understand what I mean by the cross section of that wire is cyclic. If you draw a circle, if you take a wire, this is like a wire. So the cross section of this thing is cycle. That's why we use the area of the cycle there. Alright. So now let's draw circuits now. Let's use circuits. Okay, arrangements. You know we said that how do you now arrange resistors in parallel in series? This is series arrangement of resistors. Series arrangement. Okay? So this will be R1, this will be R2, this will be R3. Okay? Now, keep in mind that when you arrange resistors like this, the equivalent resistance is going to be R1 plus R2 plus R3 plus any amount of resistance that you arrange there. Exactly. The equivalent resistance in series is always greater than even the biggest resistor here. The equivalent resistance in series for series arrangement is always greater than the resistance of the highest resistor here. Exactly. So that is that. So that is in series. Now, what is it about in series again? In series, the resistance, the current that flows across is the same. Exactly. I'm going to explain why soon. I'm going to give you what to use to remember, because students often forget. Now, what if I now arrange resistors in parallel? What if I arrange resistors in parallel like this? I have R1 here, R2, R3. The equivalent resistance is given by 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3 up to any amount of R's. Exactly. Don't forget. So if you want to minimize the resistance in your circuit, the best arrangement is parallel. This is in parallel. And if you want to increase the amount of resistance, the best arrangement is series. Is that clear? Keep that in mind. So if I say we should resolve a circuit, before we resolve a circuit, let me now explain this to you. Why is this formula like this? We know that in a circuit like this, the current that is flowing through them is going to be the same. So if the current flowing through them is the same, it means that the total EMF here is going to be IR1 plus IR2 plus IR3. Okay? So if that's the case, I'm sorry, the current will be the same. What will be different is the voltage. Sorry. The voltage across them, I'll explain how to remember it. Just stick with me first. I want to show you how this formula is gotten, okay? The voltage through them is different. So because of that, the voltage is going to be the voltage here, one, voltage through resistor 1, plus voltage through resistor 2, plus voltage through resistor 3. So voltage here is going to be IR plus IR1 plus IR2 plus IR3. So in that case, we therefore know that since the current is going to be the same, then I into bracket R1 plus R2 plus R3. Given that the total voltage is going to be current that is the same throughout times the resistance, the total resistance there. So I cancels R, and that's how the formula is gotten. But here, we know that the current will be different. So if current is different here, but voltage is the same, current will be different. So it means that current I1 will flow here, I2 will flow here, I3 will flow here. Just like V1 flow here, V2 flow here, V3 flow here. So if different currents flow here, then I will be equal to V over R, right? So V over R is our current, total current. So V over R will be equal to V, which is the same over the first resistance, resistance of the first resistor, plus V over the resistance of the second resistor. Remember that voltage is the same, plus V over resistance of the third resistor. So since V is the same, V can cancel out here, and we'll have 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3, like that. Exactly. So that's how the formula is generated. But let me now explain why it is the case, or how to at least remember it. Because some students don't usually remember when is current the same, when is voltage the same. See, listen. Look at it. Think of 3 cars wanting to pass this road. Okay? See, look at this road. Look at this road. Now look at this road. 3 cars want to pass. 3 cars. If they want to pass, Think of that car, the number of cars, think of it as the current. Why? Current is the rate of flow of charge, that is the amount of charge flowing per time. That is current. So think of number of cars as what? Current. Number of cars as current. And think of the energy of the current, or the speed. I mean, with much energy, the higher the speed here. Think of um, the amount, the speed, how fast. Okay, but to confuse you if I say speed now, because you say speed is rate of flow distance. Now, see, I want you to think of it as energy. Energy available to cars. The energy of the cars is going to be the voltage. Okay, so this my stars here are the cars. How many cars on this road? How many cars will you see every time? Every time you look at this road, any road, you will see 3 cars. You see 3 cars. You see 3 cars every time moving like this. But if you have a connection that looks like this, look at this connection. You can see these my 3 roads. They all end up here, okay? But there are 3 cars. They are following each other. They are following each other. What will happen is that the first car, if it takes this road, and this second car sees another route, it will take that route. Okay? The third car sees another route, it will take that route. So the number of cars you will see per time, that is the current you will see per time, will be the same. Oh, sorry. From here, so from here now, how many cars do you see here? 3 cars. But once you get here, the current you will see will be different, because there are 3 different cars. Okay? The number of cars you will see will be different. So if there are more than 1 car, if there are more than 3 cars, what that means is this. If there are 4 cars, 2 cars might choose to go in this way. Is that clear? So the number of cars you will see will be different. But the energy with which they flow may be the same. But in this case, the energy with which they will flow will be different. Why? Because depending on the road, if the road is not permitting them so much, they will be following each other. But if the road changes, if it's tinier, this time they will have to now slow down the more. Okay? But the road is large here. Some car will accelerate more than the other. So because of that, the energy of the car is higher here, but the energy of the car is lower here. Do you understand here? So that is voltage. Voltage across them will be different, because there will be a drop in voltage as we go. But voltage here will be the same. Voltage is the speed, the energy of the car. So the energy is still the same. But the number you are seeing will be different, because they now separate. Exactly. So that's another way to think of it. So remember. Okay, let's solve just one question, and that will be the end. Let me write the question, and we'll solve it using the concept that I just explained here, and you'll be able to understand the concept of similar voltage, similar current thing. This is still resistance, okay? Or let's do resistor rather. Let's use the box we have been using since. This one is 3 ohms, this one 4 ohms, this one 5 ohms, This one 6 ohms. Now, given that the internal resistance is negligible, calculate the resistance of, calculate 1. We've never said the voltage, the source voltage that is delivered is how much voltage should we say is delivered here? Let's just use 12 volts. 12 volts. If it's very negligible, it means it's almost 100% efficient. Okay, so let's calculate the total resistance. Calculate total resistance. And 2 says to calculate current in the 3 total currents and current in the 3 or in the 4 resistors. Okay, let's just do this. Alright, so there's this. Our battery is 100%, we're assuming it's 100% efficient. So this is the ideal case I was talking about then. This is the ideal case. What will be the total resistance? Total resistance is basically, what kind of connection is this? This is parallel connection. So what do? We do 1 over R is equal to 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6. So in this case, LCM of 3, 4, 5, 6 is going to be 12, 12, 60. It's going to be 60. 60 in 3. 3 in 60 rather. 20. 20 plus that times 1, 20. Plus 4 in this, 15 times 1, 15. Plus 5 in this, 12 times 1, 12. Plus 6 in this, 10 times 1, 10. So what do we have all together? We have 10 plus, we have 1 over R is equal to 30, 45. 45 plus 15 is 60 minus 3. 57 over 60. So the resistance is going to be, 1 over R is this. So R over 1 will now be, we take this, 60 over 57. Jesus is Lord. I was looking for a sweet number, but let's still use it. Ohms. So that's the total resistance there. What will be the total current? The total current, given that our guy, total current, given that our guy is delivering the total amount, then the EMF, which is supposed to be V internal plus V external, will now be E equal to V internal is 0 plus V external. So it will be totally V external. So the EMF is going to be IR. Okay? Total current times this. What's the total EMF deliver in the circuit of the circuit? 2 volts. Then what's current? That's what we're looking for. Times resistance, which is given, which is 60 over 57. Alright, so you cross multiply, you have 12 times this. So current becomes 12 times 57 over 60. Here 1, here 5. 5 in 57. That becomes 55. 11.2 over 5. That is 4. 11.4 amperes. Wow. That is very great. That's the amount of current that is given the voltage. Okay? That's the amount of current is delivering. Okay, well. But because the connection is parallel, so parallel connection reduces the resistance. But what will now be the current through each guy there? Current through each guy is going to be, now recall that voltage across them is the same, isn't it? So since the voltage is the same, voltage is going to be the current across 1 times the resistance of 1. Is that clear? So the voltage is the same, is 12, right? It will be equal to current, which is what we're looking for, times the resistance of 1, which is 3. Okay? Current in the 4 resistors, so that's what we're looking for. Current in 1 will be equal to I1 equal to 12 over 3. That is what? 4 amperes. So 4 amperes is going through this one. For the second one, V again is equal to I. So we'll say I2 now will be equal to V over R1. V over R1. So that will be 12 over, what is that? R2 rather. R2 for I2. So that will be V over 4, which will be 3 amperes. For I3, that will be current through the third guy, is going to be, keeping in mind that I have said it before that current will be different for parallel connection. V over R3. What is R3? V is going to be 12, R3 is 5. So that will be 2.4. Okay? 2.4 amperes. Then for the last guy, I4 will be equal to V over R4. That will be 12 over 6. And that is what? 2 amperes. By the time you add it all up together, you see that it will give you the total current that is delivered. 7, 9 plus 2, 11.4 amperes. So that will be it for this video. Oh no, that's not it. Let's quickly talk about meter bridge and Wheatstone bridge. That's where we'll stop. Now, Wheatstone bridge, was named after a certain man. Wheatstone, I forgotten his name. Now, Wheatstone bridge is used to calculate. Wheatstone bridge is used to calculate. If you need more questions on Wheatstone bridge, more explanation on Wheatstone bridge, meet me on that WhatsApp number. I'm going to explain, okay, more about it. But what we basically use to do is to calculate unknown resistance. So it's usually, the arrangement is typically like this. It's very simple to calculate, okay? So just stick with me. Now, what we'll now do is that we'll now connect a galvanometer. This is the circuit diagram for a galvanometer. Either we'll do it like this, an arrow like this, or G. Now, when do we use this? We use it when we especially are talking about a circuit component that we want to, that it is effective in, that the galvanometer is effective in. Okay, I also have a video on conversion of galvanometer to ammeter. Do it to see that video. So now what we want to do is, let's say we know the R1, we know R2, we know R3, but we don't know R4. Let's call R4 Rx. How do you calculate? What you do is, this is the last thing you do. This connection here of the galvanometer is the last thing you do. Because this one is what you want to calculate. You connect all your resistors, 4 resistors this way. You already know the resistance of 3 of those resistors is the 4th one you want to calculate. You now put your galvanometer, in between them such that it creates a bridge. That's why I call it a bridge. 2 are on this side of the bridge, another 2 are on this side. You will now find on that wire that connects them the point where this galvanometer will not deflect, will not show any deflection, to be on the 0 mark. So that point is called the balance point. That point on the wire, it could be here. So if it's here, it means we'll draw a curve here. That's the way we draw it, okay? But we like to put it at a perfect angle there. This point is called the balance point. So at balance point, there's no deflection on the galvanometer, meaning that the total resistance here is equal to total resistance here. Ratio of resistance here is equal to ratio of resistance here. Meaning also that no current is flowing through the galvanometer. Now, what you now do is this. You take it across the bridge. You take ratios across the bridge. So this is all you do. R1 over R2 should be equal to Rx over R3. Is that clear? If you do it like this, so you say R3 over Rx equal to R2 over R1. And you're able to calculate the guy. The meter bridge works with the same principle. Only that the arrangement is different. Okay? We also use it to calculate resistance. Okay? With meter bridge, what we have is we have our components. You want to calculate resist. You keep a known resistor here. Then the resistor that you want to calculate the resistance, you keep it here. That one Rx, this one R1, you already know. Now, then your battery. or your power source. Now, you will now connect what is called a constantan wire. Constantan wire is a wire um, that the resistance is consistent with the length. So it should be 100 meter in length. That's the thing with this guy. So from here to here is 100 meters. So what you now do is you now connect the same galvanometer. You put it somewhere here, somewhere across the bridge. You already know the distance from here to here. Let's call this one L1. Distance from here to here will be, distance from here to here will now be what? 100 minus L1. Because the length of this thing must be 100 centimeters. Is that clear? That's the way it is. The length varies like that with the resistance varies like that with the length. Do you understand? You already know the length of this place from this place to this place. What do you put here? I said the galvanometer. You now control the galvanometer using a jockey. What's called a jockey? So this thing here, this thing that looks like an arrow here is our jockey. What do we do with the jockey? It's simply the same thing here. You look for a balance point here. In between this resistance, and this one, you look for a point where this galvanometer does not deflect. So when you get the point, that point is also called balance point. So for this place, this will be our balance point. So at that balance point, the ratio of R1 to 100 L1 will be equal to Rx over L1. Is that clear? So see here, I didn't necessarily take the ratio across this thing. It's the same. The reason why I usually say take ratio across this thing is because you actually get the same answer, okay? But the perfect distance is to take the ratio across, but you get the same answer either way. Because here I didn't take ratio across, because you will see that if I do it like this, as R1 over Rx is the same as 100 minus L1 over L1. Look at it. R1 over Rx is 100 minus L1 if I cross multiply. You see it's the same. Alright. So that will be it. Do not subscribe to the channel and click the bell notification to get notified whenever I drop a new video. God bless you. And share the video with your friends.